Ratatsina od Menovska Mazur. I hope it was somewhat close. We'll talk about dynamic coefficients in part run failed disks with cost equations here.
Oh, there, in the corner.
Calculate model and we have partners as well, and recently there were plenty of studies which analyzed magnetic generation, large-scale magnetic generation in galaxies, and however the crucial question of dynamo theory still has not answered. And this question is, are you sure that the non-linear physical processes present in the ISM could be properly described by the mean dynamo theory? I would address some few points of this from my talk to this problem, but I think that it would be really nice if we also discuss this kind of provocative question during our discussion in the evening, if you agree on this. There are also analytical derivations of dynamo coefficients, well done by plenty of authors, starting from early work written by Hooker and Fish in the 70s, then next papers till now written by Kliolin and Rohaszewski, and they try to make analytical derivation of dynamo coefficients, but according to the nonlinear physics and really complicated story going in the ISM, it seems that they are the derivations are too simple. Also, the simulation concerning externally forced simulations and galactic boxes made by Cataneo and Weinstein, also by Axel, and have problems with quenching even with open bundles. So we decided that the best idea is to start with modeling of realistic physical processes going in the ISM, for instance MRI, as was done by Natalia, and our simulations of Parker instability, also processes. There were Miguel simulations shown today, and Marit as well. So it is possible to model the dynamo coefficients directly from computed electromotive force. The idea was first introduced by Brandenburg and Sokol in 2002. And today I would like to present comparison of the Brandenburg-Sokol method and the method which we made with our team from our Franken 70 simulations. So this is scheme of our simulation. So the evolution really was shown yesterday by Michał, and we have cosmic and shear, and as a result we have velocity fields and magnetic fields as a time series. So at each time step we can get both fields from our calculations, and then we get from this data we can calculate the dynamo coefficient and even solve the dynamo equation. This is the main equation of Michał, so I didn't explain more about them. The model is the same as Michał shown yesterday, and basic equations concerning the dynamo theory always starts from induction equation, and following method it is possible because to separate velocity to fluctuating and mean velocity the same with field, which is written here, and it results in the dynamo equation involving the mean magnetic field and velocity with electromagnetic force here, and it is defined as the mean value for cross B. This is not the mean, sorry, this fluctuation value. Fluctuates by velocity and magnetic field, and then it could be this electromagnetic force. It could be expanded in the dynamo equation. And what is important, there are alpha and beta, that's the second order, and what is important here, that there are also higher derivatives, which we have to remember that they are important also in the obtaining of dynamo coefficient. First, I would like to introduce the method of Axel and Mitya, and they try to solve the problem to get the dynamo coefficients in the simulation of box. They may make averages over that, so they got quantities which change only in Z, so also and magnetic fields is averaged over the plane, so we have only component, the first derivative here, which is over with respect to Z, and it is possible to write the total system of equations because we have such each equation, each electromagnetic force is for each time step, and then they average over the whole period magnetic field, so they got only one equation just to solve such averaged alpha and beta. Because of the assumption that there is no the conservation of flux in that direction, they have no component of C in that direction of electromagnetic force. The same, they they have no components of alpha with and beta with alpha with Z, and we apply in our simulations very similar approximation to the problem. So derivatives are only with respect to Z, not with X and Y. Why? Because all quantities which are written here, the arcs are averaged over and averaged over the planes. So it is possible to solve such an equation easily, and they make the integration over time. And our method is different. We try to apply multidimensional regression to the same problem. Just to see, we try to fit the curve, this curve which was written, which is written here. So with which we took two statistical methods to find the best fit to the assumed equations, and it is for each time step we have variable y defined with the help of a times x components. X are independent quantities, and if we take all time steps, we have also matrix here which could be written as y x is x times a plus c, and for this constant is very important here, because it is not possible to fit if we do neglect it, because this constant gives us this nonlinear part of the whole equation of
Does the dash in the last line for the v dash y for the alpha y mean something?
This
The
one?
dash.
Dash.
The
Dash
prime.
is prime. Oh, sorry. This
You waited
mistake.
that or what?
There is no prime, sorry. Should be. Excuse me.
The other primes are derivatives, right?
Yeah, it
With
was
beta.
written in
But
the...
the first line is wrong.
There is, this is proper form.
Yeah.
Oh, I would kill myself. The class constant here only. So sorry for this mistake. The results are really pressed, so sorry. So it is easy to take with the help of the least square method such solution to this problem, and which is just, you can get all these parameters alpha and beta and c, just taking few operation with x and y matrix. So it's really not complicated to get the fitting, and to be sure that we apply method which looks for the global minimum, we also check the same fitting with the Levenberg-Markov method. We found both of methods in IDL, so it wasn't problem to use them. And in this method, it is more complicated. It looks for height square minima, so we can take derivative of the height square with respect to two parameters, so alpha and beta. So we have this method which is more sophisticated, and this method looks for the global minimum in fitting. And the first results, so to compare we just choose 200 time steps, because we try to want to compare the S method and our LS, and also multidimensional regression method, and the fit of regression and this L has the same blue curve, and the averages of methods are for all methods are taken over 200 time steps, just to show the difference. So we have alpha and alpha as an example, alpha yx and alpha yy, and beta here is yxz and yyz. They all of them belong to electromotive swap, and we can see that our methods fit quite well, but the last one, because it has no constant, no linear components, doesn't work so properly. Height is much higher, height square is much higher in that case, and in the last line we have errors from the regression method to alpha and to beta as well. So there are sigmas for all values, and if we try to solve without constants, it appears that all methods are very identical, and however they do not fit the minimum, so it is not solution of fitting, so just artificial decreasing of constant. and to show the meaning of our results, we present also 200 mega years, just to show how the coefficients and constant differ. So it means that there is always a constant which is necessary to have quite large value to shift alpha and beta terms to have good fitting. So this constant really has really important meaning. And for the second, we choose also such region where this constant is very small, for 180 to 200 mega years, and the constant is small, so the solution are also.
Are you on the northern or on the southern hemisphere?
Which one? It is south. South. I didn't say that it's all this graphs were done for minus 100 parsecs. And so when the constant term is smaller, the fitting is much closer to the original curve. And we also apply this the method regression method to with nonlinear terms, and the red line looks even better than the below one, but there is no big difference. It is possible. It is possible to use also nonlinear solution for the problem. And again, we have cut minus 100 parsecs. It was chosen by Gregor, I don't know why minus, but we see that the really oscillations in alpha xx and xy as well, and the value, maximum value of alpha xx is the largest one for all alphas, not alpha yy. I will show in a moment. And also we have here for the time step 2000 layers, we have also Z distribution for one time step of this each alpha, so it is possible to see that it is under the disk plane there is positive and then more negative, and the opposite is here with alpha xy. Opposite is, and this one is certainly smaller, and this alpha belongs to electromotive force in x direction, and this they belong to electromotive force y, and we have alpha yy, which is really not big, but changes from minus to 2 kilometers per second. And we have also one maximum Z distribution from the same time step. We have one maximum or minimum, because it's minus 4 kilometers per second, and in Z then it is more or less positive, and there are also similar behavior for alpha yx. And now for eta, the largest eta are for x component as well. This is maxima of period 3 times 10 to 26 centimeters squared per second.
We had beta, right, before?
Beta. Sorry. Sorry. We made pictures in last week, so it was plenty of mistakes. We made plenty of mistakes. And that also distribution looks rather chaotic, changes from plus to minus. So about from soft loss in galactic plane, and this eta is even
What is the
small
beta, the real beta? Is only one of your components, x, y, z, or minus x, y, z?
x, y.
The magnetic diffusivity. What is the magnetic diffusivity? The main part.
The main part?
Yeah, the main part. Only x, y, z, or minus x, y, z. I don't understand. Epsilon, tensor, plus or minus. What is beta? Beta should be positive, otherwise you cannot speak about physics.
But the problem
if beta is not positive, you can forget.
this part of expansion from pi of
Yeah, no, I mean, is it minus eta in the lower corner? Is it beta or is it minus beta?
This is, in the equation, this is plus.
Yeah, but we have a very clear definition of the magnetic diffusivity.
So the question is it stabilizing or destabilizing?
Yeah.
I mean,
Certainly destabilizing.
Probably it's beta.
destabilizing, yes.
Probably it's beta or minus beta. What is it?
So apparently minus then.
Minus. Oh.
And the same here. This value is much smaller here, and not also oscillating in plus and minus. And we check how our coefficients fit to electromagnetic force, which we got from simulations, and the red curve is our dot with 200 points, and this is the green one is for 40 points, and this is the largest time interval which fit to the curve, so it is not possible to make simulations of 500 because it doesn't fit later on. So 400 is the best fit for both electromotive force, and we try also obtain Vx if Vy solving the dynamo equation very simply, and it is shown for cut 155 parsec love, and we can see that both methods, because we should compare method of VS and ours, both methods quite well could be applied. So then again, the Vx and Vy components in the obtained results. This is Vx and Vy from our calculations in second place. This. So the conclusions are that the presented methods were successfully used in calculation of the dynamo coefficients, and the method gives statistical measures, and we can estimate uncertainties, and to perform statistical analysis shows that the method gives us the best approximation of the computed electromotive forces, and that the constant is really important and also contributes to oscillation of electromotive force and could be a measure of non-linearity in the problem. Thank you.
Questions, comments?
I mean, if the constant apparently means that if the magnetic field, the mean magnetic field, is vanishing, you still have an electromotive force.
Yeah.
So I don't see the connection with nonlinearity. I would call it a battery term. I mean, if your simulation has a battery, that is some mechanism which generates magnetic field independent of the existing mean magnetic field, and it generates electromagnetic EMF without mean field, then that is battery term. Do you have any explanation why you should have such a thing?
No that we understand it as to taking into account this higher order in the equations. So this is this constant, and because of that, rather.
The higher order terms should still, if they are present, they should still be zero without if there's no magnetic field. They come in cubically in nonlinearities, cubically and without orders. Right?
Yeah. Non-linearities are involved in the normal formulation, in the sense that the alpha is a function of B, and also the beta is of course a function of B. So I agree with Axel's comment that this is, I don't understand this concept. But what I say is...
So do you have imposed field in your system or not?
Yeah.
It can be an imposed field, for example, right?
This is
No.
part of an electromotive force which does not correlate with dy, dx, and the derivatives.
The distractions of what is
Yeah.
either battery or imposed field.
Yeah,
Which is basically the same.
Yeah, but it's
appears formally, but this physical interpretation is something maybe complex. So I don't really know.
it can also be a relic of the average position. So, my main comment is, it is clear and very complicated to find beta, the magnetic divisibility. This is very complicated. And there are only a few papers about that. It is more simple to compute the alpha effect. But if only to concentrate the alpha effect. And we have some very good papers. You forgot 50% or 90% of them. For example, Ziegler 99 is a very good paper, supernova explosions, and the results are very clear, 5 meters per second. And now I ask you, do you find more than 5 for alpha in the northern part, minus 5 meters per second in the southern part? Do you find more or less than 5 meters per second? This is the question.
Similar.
No, this was the units for alpha or kilometers.
That's why I ask you, why kilometers per second? 5 meters per second.
5 meters.
Yeah, and a very high alpha xy, the escape velocity. Yeah, it is a problem, the escape velocity. Normally it exceeds the alpha effect. What is your answer for the main questions in the alpha theory? Kilometer per second and positive at the northern, negative at the southern?
Fluctuating.
Yes, of course.
Yeah, but it's no fixed only sign or...
That means you have no alpha effect in the time average. 5 kilometer or kilometer per second is the amplitude of the fluctuation.
Yes.
Yeah.
We so far haven't averaged so far because, as I said,
Yes.
we have absolutely preliminary results. So it's not possible.
Then I ask you
yeah, and
next time.
next conference I will.
Main question is does the escape velocity exceed the alpha effect? This is the main question.
Well, can you keep it here? I have a question about this topic. If it's my turn. The fluctuations obviously are strong, right?
Yeah.
But and you are using horizontal averages. Why not taking averages of thicker regions to improve statistics? So that, for example, these fluctuations in Z, obviously they are it's just noise.
I'm thinking similar to Axel, so just to compare directly to his method. So they have similar, so we have make similar. Of course, it's not problem to make average and Z lead field, for instance.
So why not splitting the whole range of Z into, say, 5 bins?
That's absolutely good idea.
Does it work? Have you tried it?
Yeah, not yet, because as I said, it is really...
Moving average, so it can be done afterwards with this plot.
But Uncle, have you tried this when you were working with me?
The problem with the Reynolds rules, as you know, if you also average in the vertical direction, so that's not so pleasant. So ideally you would like to average only over horizontal directions because of this problem. So in other words, the averages then become too dubious.
The problem with the averaging is that we cannot average too much because we want to reconstruct the final mean magnetic field Vy z component from the average quantity. So if there is too much averaging, then we cannot reconstruct this Vy z mean after from the dynamo by integration of the dynamo equation. So we cannot exaggerate with average.
And plus, again, when you do it for one slice, effectively, of course, you average over a volume whose thickness is delta z, times that. So, to that, maybe it's worth taking 3 delta z. So, anyway, you are breaking Reynolds rules.
No, you're only doing it once you have more than one. So,
Yeah. Do you have a plot of the electromotive force in X and the electromotive force in Y? And this over time and over Z. Normally it's very, very interesting. This is A method.
Electromotive force
At the given Z.
at given Z.
So, and
Original one is black.
From computations we have black curves.
And one more.
yeah, one question or a comment. We also found that the turbulent diffusivity, the relevant components of that for stabilizing, tend to destabilize, and as a consequence, therefore, as a consequence, therefore, we chose to restrict the EDA tensor such that it is only the a tensor that operates on the current density, right? So not on the other components of the B derivative tensor. And in that case, we find that it tends to be mostly stabilizing.
Okay.
So maybe.
That's a good idea to look for the defined.
Okay, let's try the speaker again. And then we move on to Hendrik Svensmark, who will talk about cosmic rays and Earth's planets.
Sometimes but you can actually push.
I guess you've tried cycling it through and down. Yeah.
Plug it out, but
Yeah, there's a little
Okay, das ist voll im Briefing. Also noch lange das kennt ihr schnell. Voll im Briefing, die noch ganz kennt ihr schnell. Before it ends.
You try to follow what they did. When we come across, show the right they were strong. Can I do that?
It should appear by now.
This now is putting here right now. And you just
We're in the center where we are. Where are we actually? Well, I don't know if we can maybe switch another computer. Tony, you want to have? Put it on the stick. I can put it on the stick, I believe. On the stick? Yes, you got it. Like 1, 2. What's the stick? Okay, Tony, can you give a hand? Is it your computer? It doesn't go up here. Use your computer.
Well, we are in the other left-hand corner.
Here, so here's fine.
Yeah.
But then it's a crazy map, right?
It's not a good map, yeah.
I was just relying on
the red line down there at the circle.
So there's there's certainly 3 different buses which go there, and unrow down 2 of the buses which are 15 and 1A, and they both go from Vienna. Is that right?
Yeah.
There's another possibility which
Where is the restaurant?
was mentioned, and it's on your map. Can you have your map again? No,
Yes.
origin.
I see.
Go at 19 minutes.
Those are not the anymore.
Oh, here's.
well, you walk past the end of the lakes. There's the lakes, so that's a scale point.
Yeah, good. Here's Maritim.
Yeah. Then the third time.
And the restaurant is there.
Sloyd is here, right?
Yeah.
Correct?
Yeah.
The easiest road there is Lebanon, the canal.
Where's the old street?
When it
The
turns
restaurant is
around,
where the circle is.
I think
it turns at the
Yeah, but,
right, and a little bit
yeah.
backward.
That's not the name. Sorry.
the street.
Yeah.
The restaurant.
That's what it is. See?
Maybe they can make one, however, nice. It's your second.
You did a point of the because it has some paintings of
Really? Inside or outside? Inside or outside?
inside.
Going to stick?
No, outside is one of these old townhouses.
Oh.
From the 17th.
Then
So whatever the big, or maybe 1801, whatever we had the last big fire.
I think, yeah. In Germany, in the architecture, in Germany is so that you can find immediately how old it is. Plus minus 10. Change from occasionally. Oh, maybe 50 plus minus 50.
Yeah, I think it's actually something like 1801, you know, the one was teaming up with the Korean, and there was a bad show, so the British came and walked and took our feet, and we've never really been good at this on being on teamed up with them all.
The conflict is
Yeah, but I think it's so much more like it also exists, but I mean, there's always
that training is also already done.
yeah, but of course it comes to land, we are really it comes to land, we are free now, right?
Europe has been given the statements and license for their time. I mean, there has been first putting this in happens, but not in the area that it's not what we think that it's spoken.
Slowly power and I'm trying to switch at the same time.
For example, my son,
You got new movies in the
but it wasn't interesting. It had been very interesting. That's why they did it 500 years later. Yeah.
Okay, sorry about the delay. Let me start. I'm going to talk about cosmic rays and the Earth's climate. And these are the persons that I have been doing this work with, and Nigel Marsh is actually here today. I've sort of divided the talk into three parts. One is, the first part is where I will try to give you some of the observational evidence that there is some kind of a link, at least between solar activity and the Earth's climate. And there are some very, very strong indications of such a link. And then the obvious question is, how does this link come about? How can this happen? And I will present you the idea, or sort of an overview of a link between what we think is cosmic rays and the Earth's cloud cover. And then finally, I will talk a little bit about climate and the Milky Way. And of course, I would be very interested to hear your comments on that part. Now, what can make cosmic rays vary? I mean, there are sort of two things, and they work on very different timescales. One is solar activity. I mean, the cosmic rays come from our galaxy. And we will have from solar activity maybe a 10% change in the cosmic rays. That's sort of the order of magnitude. Whereas if we look at longer time scales, and that will be the last part of the talk, we can have much larger variations, and that might also have some impact on the climate. Now, the solar activity is mainly, I mean, it is the shielding due to the solar wind. We have here sort of a simple schematic of the heliosphere. And we have cosmic rays that try to enter. But what is important in this context is that the cosmic rays that enters into the atmosphere, that they are ionizing the atmosphere, so they are probably important for the chemistry that's going on. They are the main source of ionization, actually below 35 kilometers. Especially over the oceans where we don't have the radioactive decay or radioactive gases. And finally, we also produce these cosmogenic isotopes, which is sort of a fingerprint of how much cosmic rays enters into the atmosphere as we can go back in time. Here you see sort of instrumental, I mean, this is actually the longest record of cosmic ray flux from an instrumental record. This is the ion chamber. It's mainly muons that has been measured. Down here you see the sunspot number. And you see the inverse correlation that when there's high solar activity, the scattering of cosmic rays is stronger, and they have more difficulties to enter into the hemisphere. We also see that there's not just a one-to-one correspondence between cosmic rays and the solar activity given by such a number here. So we can move on and go further back in time, but now we no longer have instrumental records. So what we have here is a change in cosmic ray flux. It's the last 300 years. And it's really based on beryllium-10 or carbon-14, these cosmogenic isotopes. And we see interesting that there's been a decline in the cosmic rays during the last 100 years, and we see some variations. Here we move towards the mountain minimum, where the sun was not very active. I'll say a few more words about this. But this is one of the first correlations with climate, because most people know that we have had a heating the last 100 years, and here you see this decline. And there's a fairly good correlation, without saying that there's a one-to-one correspondence. If we now move to a period of 1,000 years, here we have the carbon-14, and now I put cosmic rays increasing downwards, so we have more carbon-14 going down this way. So that means that we have a higher solar activity in the first 300 years of this, 1,000 years ago. So this was actually a warm period. It's a period where Vikings, they settled in Greenland. They stayed there for 200 or 300 years, and then they started getting problems. We got a colder climate, and we have a long period which we call the Little Ice Age, which is a period where we had small or lower solar activity. And it's, the Little Ice Age is sort of recorded in various proxy data all over the world. So this was a particular cold period in the last 1,000 years. Doesn't matter. And we have here the mountain minimum, which is famous. It's a period where very few sunspots were seen on the surface of the sun. If you look a little closer at the mountain minimum, it's from 1645 until 1715. We can look at various, one parameter that could affect climate, of course, the solar irradiance over that period. However, models of solar irradiance, although you have a lower solar irradiance, because you have no sunspots, the models that you're using are giving a very flat solar irradiance over this period. If you, however, look at beryllium-10, we see, we see actually variations which correspond to the 11-year. And then we see a sharp maximum in the cosmic rays here. Again, the axis is increasing downwards. And you see in temperature, and this is reconstructed temperatures, it's done in several ways, and that's called large uncertainties, but several of these reconstructions, they have that the coldest period, the last 1,000 years, is actually from 1690 to 1700. And there seems to be a nice correlation. So this is an indication that it might be cosmic rays. Okay. We can go even further back in time. This is data from a cave in Oman, and it's stalagmites. So you have the water that's dripping down, and you have the growth of the stalagmites. And each layer you can actually date quite accurately when you have this layer, and you can, for instance, study the isotope delta O18, which is a signal which is related to climate. And what you see over these 3,000 years, from 6,500 to 9,500, you see a variation in this climate signal in this cave. Now the top here is the carbon-14, and you see the variations that you have here match actually quite nicely with the changes in this cave in Oman. Here you see a amplification of a certain period around here, and you see that even the small scale structures correspond quite nicely. So this is more of a global signal, and this is for this cave in Oman. So this is one example of this remarkable correlation between, let's say, cosmic ray variations and changes in climate. There are many other examples that could have been chosen. And the obvious question is, of course, what could the origin? I mean, why should there be a relation? Now, we talked about cosmic rays. The energy that they produce in the atmosphere is, of course, completely negligible. It's so minute. The solar irradiance is on the order of 340 watts per square meter. Now, there is a solar cycle variation in the solar irradiance, and it's on the order of 0.34 watts per square meter. This is actually also so small that it will not have any significant influence on climate. So, if we don't think there is such a relation, we need an amplification mechanism. And this amplification mechanism that I'm talking about is what I already mentioned. Was the possibility that what if there's some relation with clouds, that there's variations in this ionization somehow could affect the Earth's cloud cover. And this is one of the first results that we got. It's from the 80s until about 95. The red curve is the change in cosmic rays. We have the 11-year cycle. And these symbols are for various satellite data sets. I think there's 3 or 4 satellite data sets. And this is total cloud cover. However, now we know that the correlation that we are seeing is really in low clouds. So here you have, it's a continuous data set. There's been some adjustments, but I'm not going to go into any details on that. But the red curve is cosmic rays, and the blue is low cloud cover. So it's clouds below approximately 3 kilometers. And we see this remarkable correlation. However, if we add normalized solar irradiance on top of it, we also see that we have a nice correlation. So we cannot just say that it is cosmic rays. It could also be some other effect of the sun's activity. Okay. So, how do clouds actually affect the energy budget? Well, on the average, we have about 63% of the globe which is covered by clouds, at least in this study. There are more clouds over the oceans than over land. But they have two effects. You trap outgoing long-wave radiation, and they reflect the incoming short-wave radiation. So you have two large numbers that you subtract, and here you get then the net radiative properties of clouds. And it's important what type of cloud we're talking about. If we talk about low clouds, we see that they have a large cooling. They cool about 16 watts per square meter. And we see thin clouds, they seem to have a heating effect, or a net heating on the Earth. So on the average, maybe about 30 or between 20 and 30 watts per square meter, we have that the clouds are cooling the atmosphere. Now, we can also look at the long wave or the cloud top temperature of the clouds. We find that if you look at a certain pixel and correlate it with the cosmic ray flux, we find that a large area of the Earth has a very high correlation. We can see what type of clouds where do we find the correlation? If we look at the temperature of the clouds and the correlation coefficient, we see that most of them have a temperature about 280 Kelvin, they're about 290 Kelvin. So these are very warm clouds, and that means that it's liquid clouds. So the correlation is found in low liquid water clouds. That's one on the jump. We can also look at the cloud optical thickness. So before I was looking at the long wave with the infrared properties of the cloud, we can also look at the optical thickness. And we can divide the cloud observations. These are all made by satellite. So we have 3 different sort of bins with height, what we call low, mid, and high clouds. And then we have different optical thickness. So here we have very thick, dense clouds. And we can have deep convective that goes, very, very high up in the atmosphere, maybe up to 10, 12, 15 kilometers or so on. And we see here that the correlation that we find seems to be fairly good in this regime as well. There are several problems with the visual observations, but nonetheless, we actually also see an effect in the optical properties of the clouds. And that's actually important because if there is a microphysical influence of cosmic rays in clouds, we will expect, let's try to take, if you have an increased ionization, we might have more what we call cloud condensation nuclei. These are the ones that are important because all water droplets are formed on aerosols and what we call cloud condensation nuclei. So if you have more of these, we might have more cloud droplets. That means we might have an increase in cloud albedo. And then what about the liquid water content in the clouds? Well, that might increase and might go down. The observation that we are seeing is that if you have an increase in the ionization, we get an increase in the cloud albedo and a decrease in the liquid water content, which has to do with the long-wave properties of the clouds. And this might be surprising. It turns out that you can make a simple, I'm jumping quite fast here, but if you have a relation between the radius or the average radius of the cloud droplets to the droplet number, how many droplets we have per cubic centimeter, then you might have a relation where you have this exponent gamma. And it turns out that exactly this relationship where this goes up, more cloud condensation nuclei, increase in cloud albedo and a decrease in the liquid water content, can be fitted for a fairly narrow regime of this lambda here. And that might be of theoretical interest, but it's really interesting that the observations of clouds actually show that almost a third of the clouds, and mainly over the oceans, are in a regime where we have this relation. So let me just summarize on these observations that we have with the clouds. We find a positive correlation with low clouds, maybe below 3 kilometers. We also find a signal in this cloud optical depth. So the effect is really, because they're so warm, it's liquid water clouds. It's mainly over the oceans where we have these marine stratars. So if you want to affect the Earth's climate, these are the kind of clouds you actually would like to change. And also that this microphysical response, if we have a change in the cloud condensation number, it seems to be consistent with what we observed. So that was the cloud cosmic ray observations. So how could this come about? Why should ionization by cosmic rays be important? Now, I told you that getting these cloud condensation nuclei is important because that's the way you get a cloud droplet. Actually, a very important mechanism is that you have certain gases, what we call trace gases. Actually, sulfuric acid is quite important, water vapor, maybe also organic vapors, that they condense into ultrafine particles and then they subsequently grow. And it turns out that the physics, what is going on in this process is actually not quite clear. And it might be that ions are important. In order to get further with this, the theory is sort of slowly being developed. Here you see some numerical calculations. So let me just explain this graph. This axis is the ionization rate. It is so that if you're high in the atmosphere, you have more ionization because more cosmic rays are ionizing. As you go deeper into the atmosphere, in the lower part, you have fewer ionization. So these colors correspond more or less to low, middle, and high part of the atmosphere. And up here we have the production of these aerosols. And if we now look, this is a numerical model, and if you look at these results, the red curve is for conditions prevailing very close to the surface. We see that if we have a change in the ionization, we will have a big, it will be quite sensitive in the formed aerosols. However, if we go to a middle cloud, for instance, it seems to be more flat if we have a response here, and even might be a negative here. So even this numerical calculation seems to suggest that we will find the effect in low clouds. So what kind of experiments have been done on this? Well, it turns out that not very many experiments have been done on ionization and the production of aerosols and the importance for cloud formation. Either the experiments you have ionizations levels that are so high that they are simply out of range compared to what we have naturally, or some experiments have been done where the trace gases are far too high compared to, for instance, the sulfuric acid concentration is far too high compared to what we have in the natural range. And at our institute, we are actually in the process of trying to investigate some of these ideas. I don't think I will go through this because of the time, but this is something that is almost built, and I can show you the chamber here. It's a big 8 cubic meter chamber, and the idea is, of course, to have good control of the concentrations and temperature and pressure and all variables that are important, and then to be able to measure the various things. The problem is that the concentrations that we have to work with are extremely low. It's part per trillion. So the sulfuric acid concentration that we will obtain in that chamber will be so extremely low that it's very, very difficult to measure. Okay, so now you have the background why we think there might be a connection with cosmic rays, and I said a little bit about the possible mechanism and that some experiments are needed. So I will go to the last part of the talk, which might be more relevant for this, and I want to start to talk about these very long time scales and changes in cosmic rays. And this is very simple. This is a work. The first part here is a work by Shaviv, published in Physical Review Letters and in New Astronomy also. That's a paper. But the main idea, the main assumption is that based on some observational evidence that there are 4 spiral arms, and of course most of the supernova explosions, they go off in the vicinity of such an arm, so that the cosmic ray flux is really located, or the source of cosmic ray flux is located close to these arms. And what he did was then to make a very simple model. We make a leaky box, and you have the 4 spiral arms, and you imagine that the solar system is somehow moving through the spiral arms. And this is solved by a very simple diffusion equation, so it's very, very simple compared to what we have done today. Nonetheless, here you see, as we go through the radius of the solar system, you see the variations that you get in the cosmic ray flux, and of course when you have this where you have the effect of the spiral arms. Okay, so this is Shaviv's calculation of the cosmic ray flux back in time. And it's increasing downwards. Again, as you've already seen, I've done this a number of times, so it's sort of upside down. So here we have a spiral arm crossing here, and so forth. The spiral arm crossing is at an interval of approximately 140 million years. So that might seems. What is the relevance with this in respect to climate? And that comes when you add the work of Weiser who is a geologist. They're trying to reconstruct the temperatures of the tropical oceans over the last 600 million years. And you see this remarkable correlation. You see when you have more cosmic rays, you have a colder climate, and you see also that, okay, the change in temperature might be on the order of 4, 5, maybe 5 degrees from peak to peak. 5 degrees in the tropical oceans, that's quite a lot actually. It's quite dramatic for the climate on the Earth. I can show you Reiser's published paper. This is from Nature 2000. You see here you have periods where the Earth is more or less in a glaciation. I mean, a very severe glaciation. You can see here where you have ice or sea ice all the way down to 30 degrees. So it is much, much more severe than the ice ages that we have experienced, or the Earth has experienced the last 100,000 years. Okay, so what about longer time scales? And what about the history of the Earth? I mean, over the past 4.6 billion years, we of course don't know what the cosmic ray flux has been. We can actually try to reconstruct it, and it can be reconstructed from how we think the sun has evolved. We know that from solar proxies. So that gives us the shielding of the heliosphere. And then the history of star formation in the Milky Way, that might give us the source field of the galactic cosmic rays. So if we do this, then start with the solar evolution. This is from studies of solar proxies, and we know from that the sun, likely was rotating maybe 10 times faster than today, so it has much more vigorous magnetic field. And the extreme ultraviolet emissions were up to maybe 1,000 times stronger than today, and the sun might even have a denser solar wind in the beginning. And all this means you had a better shielding of cosmic rays. And I've done a simple calculation using this force field approximation. Here you have present, and this is 4.6 billion years ago. And it's just the result of this solar evolution. And what we see, if we take a 5 gigavolt cosmic ray particle, that it will decrease or shield it very strongly in the beginning. And of course, this is a 5. And then as the more energy you have, of course, it's more difficult to shield against these cosmic rays. So that gives us a picture how the sun has been able to shield the cosmic rays in the lifetime of the solar system. If we now look at the star ray formation and assume that there's a relation between that and the cosmic ray flux that the solar system has experienced, these steps here are on the order of 400 million years. So we see that there's been a certain evolution. We have a peak here around between 2 and 3 billion years ago. We might have some increase again here, and we have a minimum here. If you now combine the source field and then the solar evolution, then we get an estimate for the cosmic ray flux at the Earth, sort of in a broad way. So the important thing is, first of all, that there's been a strong shielding against cosmic rays in the beginning. And then we see the effect of the star ray formation. We see we still maintain this maximum. We have a minimum between 1 and 2 billion years, and then an increase again in this period. So does it have anything to do with climate? Of course, climate is not known, the Earth's climate is not known very accurately when we go on these long time scales. It's mainly from sediments, rock sediments and so on. And as we go further back in time, fewer and fewer sediments are there, but there are certain features which are interesting look at. The top figure is the same I just showed you, and this is sort of an attempt to give you the broad idea of what happened on Earth, or the climate during the history of the solar system. On the Earth, there are these periods here where we have these strong glaciations. So this is known from sediments, and there's a long period where these glaciations seem to be completely absent. And I think it's interesting to see that there seems to be this correlation between the two. Now, there's many uncertainties in this reconstruction of the cosmic rays. One is, of course, the star rate formation, because there's been several attempts and there are large uncertainties. Many of the attempts have been, they do find a gap, and these maxima more or less. However, one may ask, why are there these peaks? And it might actually be, if you're looking at the galactic plane, where we have the large Magellanic Cloud and the small Magellanic Cloud, that at some period of time they come very close to our Milky Way, and then they have a tidal effect, and then induce make some clouds collapse, and you get an increased star rate formation. And it's interesting, if we look at the small Magellanic Cloud, and this is the star rate formation in that one, well, then we see that we have a period here where we have some induced stars or produced stars in this period here, and there's also a period here between 2 and 3 billion years ago, and then there's sort of a gap here. So this makes, and these errors is when the small Magellanic, or this system was closest to the Milky Way. So this could be such a induction. It's of course interesting that we see both in these Magellanic clouds and in the galactic plane some of the same features. So that makes you think that these peaks, it gives some support to them. So let me just show you. This is just another example of someone who's been trying to reconstruct the star ray formation in the Milky Way. And here, it only goes 2 billion years back, and you see that there's sort of a higher resolution. And the question is whether, it might be such interactions that between these dwarf galaxies and the Milky Way, parts of our local group, that are making these inducing increased star ray formation. So let me conclude. Particles from space, they seem to influence the Earth's climate, and on very short timescales, these solar cycle lengths on the order of at least 11 years, and maybe even to these very long timescales. That might be a suggestion from the data we've seen so far. And of course, it means that the processes that are going on in the Milky Way, they could actually be quite important for the evolution of what is going on at the Earth, because these climate changes that we see, they are very dramatic. Some of them, they are these snowball Earth events where it's believed that most of the Earth has been covered by ice. I don't suggest that it's the only cause of climate change, of course, and the real question is how this minute energy from cosmic rays can affect processes in the atmosphere. And that's where we need this physical mechanism, and we believe that it could be through these clouds that we see these correlations, and that the microphysical mechanism might involve this aerosol formation, so you get these cloud condensation nuclei. And I think that if you understand this thing, it could actually have these large implications in our understanding of climate changes. Thank you. Okay. Questions?
First are these data consistent with meteorite data? Because I seem to recall that they say that the cosmic ray flux was more or less constant over the last 2 gigayears. So.
Yes, in the paper by Chile, he looked at these iron meteorites or whatever that drop down on the Earth and looked at, and he finds first of all, a 140 million year period in them with the right phase compared to these spiral arms. This idea of the spiral arm passing. So there seems to be a consistency in that. And of course, these data, these results have been questioned and so on, but it's just an ongoing debate. But nonetheless, you actually see a 140 million year period in them, which is, first of all, why 140 million years? It was just by accident. And secondly, that the phase is right also. So there seems to be some consistency in that.
And the second question is, if you look at these long time scales, the solar system also must pass through regions that are denser, and so the heliosphere must be actually smaller than, and that should also affect the cosmic ray flux.
Yes, there's also been work where, if you go through a denser cloud, the heliosphere will be contracted and you will get a higher cosmic ray flux. On those timescales that I was looking, 400 million years, then these are very high frequency events, I would think. So, the probability of going through these dense clouds is probably higher if you're in the spiral arms and if you're outside, and depending on where you are in the galactic plane as you move around and so on. But that will also have an effect, and there are speculations about it. I don't know if there's any evidence that sort of illustrates that that is the case. It might be difficult.
Well, about modulation of cosmic rays for the spiral arms, they say it was briefly touched. We understand correctly that there is no much evidence for such modulation from gamma rays, although it is so that whatever is how. Because Habib assumes factor of 3, I think, changes in the arms.
Of density or what?
Cosmic rays in arms, between the arms. It seems to be that.
Well, you mainly have the source in the. The source of cosmic rays is there, and you get this because of the diffusion, right?
The diffusion is strong, but they diffuse out.
It would be really interesting if you could say that picture is wrong.
Also the spiral arm model, I don't know which one they use, but the version of the classical one, it's very absurd, this spiral structure. It hasn't been, last year also a new spiral structure. I think it's quite different from the old.
Yeah, I know that there's no consistent picture about the spiral arms. Many people think that that's a very uncertain part of the whole thing. But then we have this iron meteorite evidence that maybe support that this is the case. There are some observations. There was a paper by the review a number of years ago with the spiral arms, where at least they see 3 of them, and the fourth is blocked because of the center of the galaxy. So, there are some support for it, and then there are some things that doesn't fit very well. With respect to the things I've been showing with the star reformations, there are also some new results with star reformation that does not look at all like what I've been showing here. And that was why I put this thing up with the Magellanic Cloud, to see that there was actually also a peak in them at the right time when you had an interaction. So I think that's there's many uncertainties in this. That's true.
I have another here. Some comment about the solar spin down. It's true.
Excuse me, what was that?
Spin down.
The sun.
The sun.
Yeah.
Solar spin. It's true that the young sun had probably a sure rotation time of 2 days, and now we have 25 days, and so forth. We believe that this spin down was continuously after this Khomeini law T to the minus 1.5%.
Yeah.
But now new observations of a lot of clusters of different ages show that the rotation rate of the solar type stars, and of course also their activity, magnetic activity, was constant over the last 1.5 gigayears. And at the beginning there was a very intensive rate of the rotation, and then 1.5 gigayears.
How long time was it going down, you think?
I speak about 5 gigayears.
Okay.
And in the last 1.5, nothing happened with this. by the observers. The original observation of Skumeni's work, he had only two clusters. They have Pleiades, Hyades in the sun, not a cluster. And now we have a lot of observations in clusters of different age, and then you find that this is such a function.
Okay.
So that over the last 1.5 gigayears, the activity, the magnetic activity of the sun should be uniform, rather uniform.
But 1.5 is short compared to 4.5 or whatever, the age of the sun.
4.6.
Yeah, 5, yeah. It is short, so it is short.
So if you say it like this,
Yeah.
then this should be longer than this, right?
Yeah, but for the models it's interesting. Over the last, the climate in the last gigayear must, for the simulation, must take into account that the rotation was practically constant of the sun. The activity, the magnetic activity.
I also would like to say that this variation of the cosmic ray intensity in the spiral arms is not true. If you do simulations and you look at the supernova exploding 30 parsecs away from our solar system, you will see that the cosmic ray intensity increases by 20% or more. And if the supernova is away maybe 50 or 60 parsecs, you see only variation of the level of a few percent. You have the diffusion, but this diffusion acts that you don't see anything if you are maybe 100 parsecs away from the supernova.
I was saying that it's easier for the cosmic rays than to escape vertically rather than to propagate towards the sun.
Coming into the equipotential argument from yesterday, the magnetic field variation is stronger in different arms and in arms.
But not
Only two more questions, right? So there was Patrick and there was Keith.
Yes, I was wondering, you showed these plots about cloudiness and correlation with the solar activity, but now that's connected to cloudiness, so is there direct data of ionizing radiation and solar activity so that you compare? I'm just wondering if it is solar cosmic rays that you create that penetrate deep in the material, or what is causing this?
It's definitely not solar cosmic rays.
So it's something that comes out.
It is galactic cosmic rays that are making this ionization. I mean,
And then it's muons that ionize.
below 6 kilometers, it's probably changed over and becomes many muons that are
Right.
ionized.
So it's actually the solar wind that somehow changes, and then
It's a solar wind that modulates.
yes, the same way as you had for this longer time scale. Okay, so it's high energy cosmic rays actually, not the low energy solar.
It's not the low energy, no. I mean, also
high energy, I mean something like 10 GeV or something.
I would say that the typical energy, at least what we think now, is on the order of 10 GeV. That's
Yes.
the one that ionizes in the lower part of the atmosphere.
Right.
So,
Yes. And last question.
The climatology question, I always thought it's not so clear what the clouds, which role the clouds play in the climate. I mean, water vapor is also greenhouse gas, so increase in the number of clouds as necessary is getting cooler, no?
yes.
I thought this is a complicated question because if the jet is linked that if you increase the cloud power, then you cool down the climate. So I thought this is not obvious.
Yeah, I mean, clouds are the least understood on the climate models. I mean, there's no climate model that actually can include clouds in a proper way. They all get it wrong. So I think there are room for surprises. Okay, thank you. Let's continue the discussion.
So for everybody with a name tag, the lunch will be free. Somebody doesn't have a name tag, even if you have it upside down. Yes, sir.
I was going to do it.